We're really pleased to welcome Jeanette Wing to present today in our Distinguished Lecture Series. Her talk is Data for Good, which really goes very well with our push for our new vision statement, Computing for the Common Good, and also our Equate group, which is working hard on safety and fairness in AI and data science generally. And I'll do a more complete introduction, but I was going to tell this little story. So Jeanette and I shared an office as graduate students. There were 3 students to an office, there were 3 desks, and there was one terminal. It was a VT52, 24 row, 80 column, clunk, clunk, clunk kind of thing, connected to a machine probably less powerful than your cell phone. But anyway, I would get in early, I guess because my wife had a job that started early. And I would be there and I'd be hogging the terminal and probably frustrating Jeanette and my other office mates some. But there's a way in which she sort of got back at me years later. And this will show a little bit of Jeanette's sense of humor. She knew that I like spicy Asian food, and I was visiting her in Pittsburgh at Carnegie Mellon. And she said, I know this great Thai restaurant over in Oakland, the next, I don't know, neighborhood over. And so we went there and she was like, yeah, they do it on a scale of 1 to 10, you know, go for 10 in the hotness and all. And I said, no, that might be too risky. And she said, no, go for it, go for it. So I did, and it's, I think, the only Asian food meal I could not finish. It was too hot. So I think that was Jeanette getting back at me for hogging that terminal all those times when we shared an office. Anyway, so that's my little story. Now let me get to the actual introduction. So Jeanette M. Wing, she's currently the Avanessians, I think I'm saying that right, director of the Data Science Institute and professor of computer science at Columbia University. Now, prior to that, for 4 years, she was corporate vice president of Microsoft Research. She remains an adjunct professor of computer science at Carnegie Mellon, where she began in 1985, the same year I started at UMass, actually. So we're very contemporaries. She twice served there at Carnegie Mellon as head of the computer science department. Now, a little earlier, somewhat before she was at Microsoft, she was assistant director of the Computer and Information Science and Engineering Directorate at the National Science Foundation. And she received all her college and PhD degrees from MIT. And she has numerous awards. Let me just mention a few. So she's received Distinguished Service Awards from the Computing Research Association and from the ACM. And she's a fellow of the American Academy of Arts and Sciences, American Association for the Advancement of Science, the ACM, and the IEEE. We'll virtually applaud, I'll applaud for everyone, welcoming Jeanette, who's going to speak on Data for Good. Thank you, Jeanette.
Thank you, Elliot. And if someone asks me at some other time, I have many Elliot stories to share with you. So let me begin.
Well, let me just dive in and tell people the protocol for question answering. I should have done that up front. So there's a Q&A thing available on Zoom webinars. The chat will not be enabled for you, but you can ask questions on the Q&A. And we can either answer them there, I can pass them to Jeanette, or depending, I may be able to turn on your mic to directly ask your question. All right, go ahead, thank you.
Thank you, Elliot. So I'm going to talk about data for good, ensuring the responsible use of data to benefit society. Let me start by framing data science in what I like to call the data life cycle. So of course we generate lots and lots of data. Generation of data is not new. If you think about the scientific disciplines, which have been collecting and generating lots of data through their scientific instruments, whether they be large telescopes pointed to the sky or satellites going around, or exploration instruments searching to the edges of the universe. Also, large neutrino detectors in the South Pole, and so on and so forth. These are large scientific instruments. The science community has been generating tons and tons of data for decades. What is new, of course, is the generation of data about people. That is, we are generating lots and lots of data through our cell phones, through our online interactions through the web, and also through our physical interactions in the world, in the real world. We generate more data than we can personally collect, but others collect data about us. And of course, there are lots and lots of third parties that collect this data and use this data to provide free services and so on to our benefit. Not all data is collected, not all data generated is collected. And then there's processing the data that is collected. Now, by processing, I include everything from encryption to compression, but also the more mundane tasks of data science, including data cleaning and data wrangling. We finally do store the data somewhere on some medium, and we store the data in such a way that we can retrieve the data efficiently later, and that's where all the database management techniques come to play. Data analysis is, of course, what is making data science so exciting these days and why there's so much attention on even this emerging field called data science. And that is the machine learning, the AI, and the statistical techniques that we use to analyze the data that we have generated. Now, it's not enough to analyze the data and spit out probabilities. It's important to actually visualize this data in some meaningful way. So data visualization is very important for the end user. It wasn't actually until I joined Columbia University 3 years ago, when I was talking to my friends in the journalism school, that I came to appreciate the step that I call interpretation. It's obviously not even sufficient to visualize the data through a pie chart or a bar graph. You actually have to tell a story about, well, what am I supposed to get out of that pie chart or bar graph? You might have the prettiest visualization you can imagine, but if it's not meaningful to the end user and the end user doesn't know what the point of that is, then it's still pretty useless. And finally, throughout this entire data life cycle, I want to stress the importance of privacy and ethical concerns. This is something that I believe the computer science community has gotten onto a little too late, but I feel like with data science as a new and emerging field, we can get this right from day one. Now, what is data science? There is no consensus definition of what data science is, and there isn't even a consensus of whether it's an academic discipline. It kind of reminds me of the old days when computer science was first starting, and some of us are old enough to be around when there were no majors in computer science and there are just a handful of departments in computer science. And I see something similarly happening with data science. So what is data science? I do like to give a succinct definition. It's a working definition, which seems to really appeal to a broad audience. I define data science to be the study of extracting value from data. There are two important words in this definition. The most important word is the word value. Value is subject to the interpretation of the end user. So value to a scientist is actually discovering new knowledge. Value to a business is actually bottom line. How many times do people click on this link? Because each time someone clicks, I make some money. My data is an asset to my company. And value to a policymaker is tremendously important these days when we think about societal challenges like climate change. You know, a policymaker, some local mayor is going to want to know what kind of zoning laws to put into place if if hurricanes or floods are going to wreck the coast of, say, North Carolina. So it's important that we make new policy based on data. The second important word here is the word extracting, and that is, of course, what all of us do in computing and statistics and so on. And that's a lot of hard work to get that value out of the data. So I want to share with you the three-part mission statement for the Data Science Institute at Columbia University, because I'm going to be using this to index the stories I tell about how data science really pervades all disciplines. The first is to advance the state of the art in data science, and this is really to push the frontiers of basic research in this new emerging field of data science. At Columbia, we define the foundations of data science built on three pillars of strength: computer science, statistics, and operations research. Obviously, a lot of the work going on in OR and optimization algorithms comes out of the OR community. At Columbia, we have a very strong OR department in the engineering school and a very strong OR division in the business school, and they work very closely together. So OR happens to be a strength at Columbia, along with computer science and statistics. So it already is multidisciplinary data science, if you think about just the foundations of data science. And of course, we also appeal to signal processing from EE and analytics from applied math. And so even just the foundations of the field is multidisciplinary. The second part of my mission statement speaks to the full-fledged nature of Columbia University, and that is to transform all fields, professions, and sectors through the application of data science. When I first joined Columbia 3 years ago, I thought I would have to go around talking with all the deans and department chairs and cajole them into the importance of data science for the future of their field in terms of research and education. It's been just the opposite. Whenever I would meet with these people, they would say to me, you know, Jeanette, I have this really interesting data set, but I don't know what to do with it. I need some data science expertise. And so it's been high demand for very few faculty and researchers to go around, but that's a good position to be in. And I'm sure the same is true at UMass Amherst. And then the last part of my mission statement is indeed the title of my talk, and that is to ensure the responsible use of data to benefit society. I mean two things by this statement. One is to benefit society, and that is to tackle societal grand challenges like climate change and healthcare and energy and social justice. These are sorts of the big problems that an academic institution and the faculty and students within really strive to tackle in research and education. It's the other part of this mission statement that I'm particularly proud of putting in when I first created it, which is that ensure the responsible use of data. And by that I mean the privacy and ethical concerns in using data. And I'm going to return to this point later and elaborate. So I summarize my mission statement into 3 words: data for good, data to do good for society and humanity, and using data in a good manner. So I mean data for good in both senses. We are highly collaborative. We are a university level and a university-wide institute. We're one of 3 such institutes at Columbia University. We collaborate with every single other school and college and institute on campus. We have over 350 affiliated faculty, and they truly come from all the disciplines in arts and sciences and engineering, but also the professional schools like journalism, the law school, the business school, all the medical school campuses, schools in dentistry, nursing, public health, and of course, physicians and surgeons, the School of Social Work, and so on and so forth. We even collaborate with Barnard and Teachers College, if you're familiar with the Columbia structure. So this is quite a fun playground to be in. It's really, sometimes I think my job is just connecting the dots, but it's really impressive to be able to meet so many people across campus and recognize that so many fields and departments are really trying to push data science forward in their own disciplines. We roughly have various cross-cutting centers. I don't want to really dwell on this, but just to say that there's some obvious ones like foundations of data science, health analytics, financial analytics, computational social science, and so on. One program that we run jointly with Columbia Entrepreneurship is something we call the Collaboratory, where we ask faculty from 2 or more different disciplines to come together and co-design and co-teach a brand new course that's basically on the books. And we have over 26 such courses that have been operational for the past couple of years. There are 2 I wanted to point out. One is an undergraduate course. It's a gentle introduction to data science called Data, Past, Present, and Future, and it's co-taught by an applied math professor and a history professor. It's not a rinky-dink course the first day. All the students open up a Jupyter notebook, and they're learning how to read code. But remember, many of these Columbia College students don't have a highly technical or quantitative background, so they're not at the end necessarily writing code. The other success story, oh, by the way, I wanted to also mention that this particular course is now, it satisfies the science requirement for the Columbia College students and the non-science requirement for the Columbia engineering students. So that's kind of a fun fact. Another success story I wanted to share with you through the Collaboratory is an 8-course sequence in data science that the current dean at the business school actually invented. And through that curricula, I would say now 50% of all Columbia Business School students graduate with some data science knowledge. And so this is quite a feat. And when I talked to the dean, he said it could be 100%. It's just a matter of capacity. We have a very robust industry affiliates program. At any point in time, we have about 25 companies that are part of the industry affiliates program in the Data Science Institute. And we are international. We have Chinese companies, Brazilian companies, a Spanish company, and they represent all different sectors, from media to IT to pharmaceutical and retail. We also have a deep relationship with IBM. This has been a center that I helped create with the School of Engineering on blockchain and data transparency. There's a research thrust, an education thrust, and an innovation accelerator. So now what I wanted to do is share with you some of the research that goes on in the Data Science Institute through the faculty and students and postdocs. I'm not going to be able to be comprehensive, so I'll just give you a little snapshot of various stories. Let me start with one story on advancing the state of the art in data science. And it has to do with causal inference. Classical causal inference considers univariate causes, for example, whether a subject receives a drug or a control. In this particular work, Yixing Wang, who's a postdoc of David Bly, and David address a different situation. They consider the situation where there are multiple causes for an effect. And it turns out that not only is this a common scenario, if you think about the real life, it's not just a single cause for an effect. There might be multiple causes for a particular effect. But it turns out it's actually an easier problem to solve with weaker assumptions than for classical causal inference. So let me first start with an example to motivate, the story. So suppose I'm a producer and I want to understand the causal effect of putting an actor in a movie that I'm going to produce. I have to make casting decisions and I want to predict the expected revenue. So do I put Sean Connery in a James Bond movie and will I make more money if I do so than say if I put Roger Moore in? My goal is to estimate the expected revenue given a particular cast A. So I want to estimate the population distribution of Y of A, and thus for a particular cast A, estimate the expected outcome. Now, the expression I show here is how the statisticians would express the potential outcome for a causal effect. For those of you who are more familiar with Judea-Pearl's do calculus, this is how Pearl would write it in the do calculus. So a naive approach to this problem is to fit a regression from actors to revenue. This would estimate how much revenue changes when an actor is included. However, the canonical problem with causal inference is that there might be unobserved confounders. These are variables that affect the causes and the effect. So in this case, they affect the cast, the people I would put in the movie, and the revenue, how much money I would make. For example, the genre of a movie could be a confounder. And as action movies make more money than artsy movies, whether a movie is a sequel or not is a confounder. Some actors, when appearing together, might generate more revenue if they only one were cast, and so on and so on. So there are multiple possible confounders to figuring out cause and effect. Confounders actually bias the regression coefficients. So some actors will be overestimated and some will be underestimated. So before I walk through how Wang and Bly address this problem, I just wanted to argue that, of course, there are many applications where multiple causal inference bears its head. How do genes affect a trait? The causes of their genes. The effect is a trait. How do sports players affect how well a team is doing? The causes are who is in the game. The effect is the points scored in the game. How do prices of items affect how much money is spent? The causes are the prices of each item for sale. The effect is how much money is spent. So now let's look at classical causal inference, and then I can share with you how Wang and Bly address multiple causal inference. In classical causal inference, there are really three steps. The first is you think about all the confounders. And then the second step is you measure the confounders. Those are the W sub i's. And these are the variables that are dependent on both the assigned potential causes, the actors, and the potential outcomes, the Y's, the revenue. Now, if we can measure all the confounders, then we can append each W to each data point in our movie data set and estimate an iterated expectation, which is the right-hand side of the equation above on the right. And this step essentially corrects for all the confounders. And this three-step process is the canonical way that classical causal inference is expressed. But this only holds under a very strong assumption called strong ignorability, which says that there are no unobserved confounders, which means you have to have thought of all the confounders. And this is a big assumption. Well, we can, we're human beings. We never know when we might miss something. So this is all of classical causal inference rests on this assumption. And what makes it harder or worse is that this assumption is untestable. So that's a famous theorem that one can't actually test whether you have thought of all the confounders. So what is the new idea? The new idea exploits the multiplicity of causes to sidestep the search for all confounders. So first, there's a three-step algorithm here. First, you find a good latent variable model of the assignment mechanism, where Z is a local factor. Here, the A sub ij's are the observed assigned causes, indicate the binary variables indicating which actors J are assigned to movie I. Then we use this model from part one to infer the latent variable for each data point. And then, just as we did with the W's before, these new latent variables, Z hats, are the substitute confounders. We plug them into the right-hand side of that estimating causal effect expression by correcting for the substitute confounders to do the causal inference. So the deconfounder replaces an uncheckable search for possible confounders with the checkable goal of building a good model of assigned potential causes. And the punchline is, if we can find this latent variable model or factor model that captures the population distribution of assigned possible causes, then we have essentially discovered a variable that captures all those multiple cause confounders. Now, there's no free lunch here. There's still an assumption, but it's weaker. And that assumption is that there's no unobserved single cause confounder. So before, there was a strong assumption where there are no unobserved confounders. Now we just assume that there's no unobserved single cause confounder. So let's go back to the movies and see how, by building the deconfounder, it affects the values of Sean Connery and the actors who played the characters M and Q in the James Bond movies. So it turns out that if you looked at the data that I showed you earlier, Sean Connery's value with the deconfounder goes up, and the actors who played M and Q, their values go down. What this means is that without the deconfounder, Sean Connery's value was underestimated, and Bernard Lee and Desmond Llewellyn's values were overestimated. And now that we have this model, just like for causal inference, we have a model that we can ask and answer other what-if questions. That's the whole point of doing causal reasoning. So hold this basic thought of a deconfounder in your head, because I'm going to return to it later as the last story in my talk. But now let me move on to this second mission statement of mine, which is to transform all fields, professions, and sectors through the application of data science. And let me first start with a science that's very obvious in terms of big data, and that is, of course, biology. I would say it's really when we were able to so successfully sequence the human genome that I think the biology community recognized not just the importance of computer science, but the importance of data. In this particular work that my colleagues at Columbia and others have done, they looked at the pancreatic cancer tumor, and they recognized that the microbiome surrounding the cancer tumor cells were actually counteracting the effect of the chemotherapy treatment of the cancer. So that's not good. What they further did was they discovered that if you inject the tumor cells with an antibiotic, then that would counteract the effect of the microbiome, therefore making the chemotherapy treatment effective. And this is all through looking at genetic data of the microbiome and the cancer cells. For a different science, there's a lot of, I really want to commend the astrophysics community, astronomy community for being so courageous. They typically will embrace any new method that comes along, and they have definitely embraced machine learning and AI. This particular work was to assess the performance of convolutional neural networks to predict the cosmological parameters of the lambda cold dark matter model from weak gravitational lensing data. And what they discovered was that CNN, sure enough, actually predicted the coefficients or the parameters of this model far better than off-the-shelf statistical techniques. When they first discovered this, it was just as with all neural networks, it was still a mystery as to why it was so good. But in fact, CNNs outperformed those statistical techniques. For something completely different, I wanted to talk about economics and machine learning. In my time at Microsoft, I actually hired a bunch of economists in Microsoft Research because we all recognize the importance of economics and computer science, and they were actually the ones who really spearheaded the movement within the company to bring big data and machine learning to the thinking of economists. Economists, by the way, want to infer causality. They want to know that if I increase the prices, the revenue will go up or down, or something will happen. And they want to know that it's more than a correlation, but they really want causality. And they typically use these these methods using instrumental variables to build these models to determine causality among the various variables in the model. What I learned at Microsoft was a collision of causal reasoning by the economists and big data from the machine learning community really was a new way for both fields to leverage each other's strengths. And I actually saw business impact with these two communities coming together. The work here that I'm going to share with you has more to do with online markets, online labor markets like Amazon Mechanical Turk. And here, my colleagues at Columbia and also at Microsoft Research looked at Amazon Mechanical Turkers in the US and in India and analyzed a lot of the big data that was coming through the transactions that they did on all the tasks that they performed. And they wanted to understand what kind of market behavior these Turkers basically manifest. And what they discovered is that they behave more like monopsonies than, say, a fair market. A monopsony is when you have one buyer and multiple sellers, as opposed to a monopoly where you have one seller and multiple buyers. They found other interesting behavior patterns by looking at the data. For instance, one might think that Turkers would go after the high-paying tasks because you kind of get more money per amount of work that you do. But in fact, Turkers tend to go for a lot of low-paying tasks. And I guess by doing a little work and doing a lot of little work, you still get a lot of money. In another area related to finance, there's colleagues of mine looking at robo-advising. So if you happen to have a personal financial advisor, you know that it takes a while for your advisor to learn your investment preferences, whether you're risk averse and you put all your money under the mattress, or you're quite risky and you put all your money on the stock market and other instruments. So in robo-advising, using a pretty standard reinforcement learning algorithm, a robo-advisor can actually learn an investor's preferences over some number of iterations of a particular reinforcement learning algorithm. And in this case, it was 8. And it really is really an example of automating something that is manually takes months or years to perform. And something completely different in our history department, I already mentioned a history professor who co-teaches the Data Past, Present, and Future course, but a different history professor has been amassing the largest declassified documents from the US government over the years. And what he does is he and his colleagues use machine learning and sentiment analysis and topic modeling and other data science techniques to analyze these documents. In this particular work, they were looking at the cablegrams that were sent among diplomats around the world in the 1970s. They were looking at the two from subject and the body of the cablegrams. And what they wanted to do was they wanted to know whether they could discover the interesting events, to figure out what were the historical events during that time period by just looking at the cablegrams. And sure enough, they were able to distinguish between topics describing business as usual and those that deviate from such patterns, which they identify as historical events. So each black dot here is such a historical event, and you'll recognize some of them, like the evacuation of Saigon and the death of Mao Zedong. So now I want to turn to the last part of my mission statement, which of course has 2 parts, and I'm going to divide that discussion into 2 parts. One is data for good, the responsible use of data. And I wanted to share with you a big agenda that I've started trying to promote for the computer science, AI, data science, security and privacy communities, formal methods community, it goes beyond, just trustworthy computing and so on. And this is a push I call Trustworthy AI. I think this speaks to some of the remarks that Elliot made in his opening when he introduced me. So I've been working in trustworthy computing for a couple decades now, and I remember when it first really started emerging from various National Academy reports, from various programs that the National Science Foundation started and continues to support through the Secure and Trustworthy Computing Initiative, and also from the first Bill Gates memo called Trustworthy Computing that he put out in 2001 when he was still running Microsoft. And trustworthy computing has come to mean various properties of computing: safety, security, privacy, reliability, availability, and usability. We continue to pound on making sure that our computing systems are more trustworthy. As attackers get more sophisticated, it makes our lives harder. But there's some areas where we've made tremendous progress. And I think with all this interest in AI systems, we have now upped the ante on all of us, especially in computer science and AI and data science more broadly. For one, we've upped the ante in terms of what does trustworthy mean. I think for AI systems, of course, we mean safety, security, privacy, reliability, availability, and usability. But there are new properties that all of a sudden we really have to tend to for AI systems. We talk about accuracy, robustness, fairness, transparency, accountability, interpretability, explainability, and even ethics in AI. Some of these properties are formalizable. We can write a mathematical expression for defining the property, and then we can work really hard to see whether an AI system has it or not. Some of these are harder to formalize. That was true even in the trustworthy computing days. So trustworthy AI ups the ante in terms of the kinds of properties that we have to worry about. And the other way it ups the ante, of course, is that AI systems are not your typical computing system. There's a lot of probability and statistics that underlie the nature of the AI systems, stochastic processes, nonlinear functions, you name it. The AI system is not a typical hardware or software, somewhat deterministic system to reason about. So what I wanted to focus on are a few examples of some work that we're doing at Columbia, some work that I'm actually doing on some of these properties. Some of them are looking at trade-offs between these properties. But I really am very excited about trustworthy AI, and I can just imagine many people at UMass Amherst are interested in these topics too. So let me start with some work that I've been doing recently with some colleagues of mine, a graduate student, and postdoc. We've been looking at this trade-off between robustness and fairness. I'm assuming many of you are familiar with the controversy that ProPublica raised in terms of the fairness of risk assessment tools that are used in US courts today and how they are unfair. That, of course, led through a whole line of research done by computer science and economics faculty on understanding what fairness actually means and recognizing that there are multiple notions of fairness. And if you formalize them, you'll immediately see that some notions of fairness are actually incompatible with each other. This, of course, again, ups the ante for all of us in computer science because we all can agree on, what, say, safety and liveness means in terms of temporal logic formulation of correctness for a concurrent system. So fairness it already raises lots of interesting questions and challenges for us. So the work that we did very recently, and it's going to appear in NeurIPS in December, looked at state-of-the-art FAIR classifiers, which we used on this particular COMPASS data and 3 other data sets. We recognize that these classifiers are not very robust. What does that mean? It means that what we did was we took the input data distributions and we very slightly reweighted them, and we could make that, quote, FAIR classifier basically unfair. It would be classifying things incorrectly. And you'll notice that the reason that you don't see much of a difference between the red bars and the blue bars is the point, that the reweightings are very slight. And so these classifiers are very fragile. So what we did was we used an online algorithm. This is pretty canonical now in the field for making machine learning algorithms fair. We used an online algorithm, a 2-player game, to build a fair classifier so that we can argue that the fair classifier is actually robust to a class of distributions. And this is something that allows us to make a stronger statement about a particular classifier. But of course, there is a trade-off with accuracy. And the second example I wanted to share with you has to do with a system called Deep Explore. And this is for testing deep learning systems. And I think the reason I like this example is that the work was actually inspired by 2 techniques from software engineering. One is code coverage, and their analog is neuron coverage for DNNs, deep neural networks. And the other is a notion of differential testing, where you have 2 pieces of code that are supposed to perform the same function, but they're different. So they take 2 different DNNs that are supposed to classify the same set of images, and they do comparison. And using these 2 techniques inspired from software engineering, they built this Deep Explore system. And they showed that all the state-of-the-art DNNs for ImageNet and self-driving cars and so on can really be easily fooled by very simple perturbations of input images. These are simple but actually natural perturbations. So for instance, in the picture you see on the left, if you just slightly darken the picture, which would be a normal sort of thing that you would imagine a self-driving car to have to encounter, because you don't drive just in daylight, you drive it at dusk and you drive at nighttime, the classifier would actually tell the vision system, instead of veering to the left, to veer to the right. And then you fall off the cliff and you die. And so then this work was also shown for non-image examples, for instance, PDF and Android malware. Another reason I like this work is that it got the SOSP, Best Paper Award, and it really goes to show how machine learning and AI and data science have really pervaded throughout the entire computer science community. Another piece of work I wanted to share with you is actually, again, trying to make DNNs a little more robust to input perturbations. But this particular work approaches it differently. So in the previous work, you have a DNN and you're basically testing it, and you're finding some test cases that make the classifier behave improperly. It's kind of like testing after the fact. Well, in this particular work, suppose we could construct the DNN to be correct by construction. That's the other kind of software engineering approach that we all know and love. And the way that this work by Roxana and her students handle it is to actually, inspired by the notion of differential privacy, they add a layer of noise in the DNN. And in fact, they found that adding the layer after the first layer is a good place to add the layer. And by adding a layer of noise, you can control the robustness. You can control the amount of noise you add, and then therefore you can control the output to be certifiably robust within some error bounds. And I really like this work first because it's like inspired by differential privacy, but it's applied to DNNs, and it has to do with robustness. So it's really quite a beautiful combination of ideas. Now let me turn to some of the work that we do at Columbia that tackles big grand challenges, if you will. Let me start with something pretty obvious, which is climate change. There's a huge effort in the Earth Institute at Lamont on building an open source platform to support climate scientists, in this particular case ocean scientists. They have quite a sophisticated layer of open source tools in this platform that now allow climate scientists to do simulations for ocean currents, hydrology, meteorology, and so on. This is quite a large collaboration. It's all about big data. The second example I wanted to share with you has to do with data science in agriculture. In this particular work, the researchers, the data scientists were working with policymakers and climate scientists in India to understand, what are the effects of climate on grain production. In India, most of the grain planted is rice, because it's one of these chicken and egg things. Most people eat rice, so you plant a lot of rice. And you plant a lot of rice because most people eat rice. But climate changes that may be coming or are already here in India are suggesting that there should be, policy should revisit how much rice is planted. And they looked at 6 different grains, including rice, and they basically concluded that if India's crop production continues to homogenize towards rice, the food supply in the country may be more vulnerable to increasingly frequent climate shocks like droughts and extreme heat. It turns out that the monsoon seasons are also changing in India, and how much rain happens per monsoon is also changing. And these are examples of these climate changes that the farmers need to be sensitive to as in the future, and the government needs to be sensitive to in terms of being too reliant on just one crop, one grain, that being rice. So they also looked at, as I said, 5 other grains, and they suggest that increasing the share of production contributed by coarse cereals like millets and sorghum could improve the resilience of India's food production against climatic changes. And so this is an example of data-driven policymaking. Now, I don't know that the Indian government has adopted any new policies, but this is the science that would speak to that kind of new policy. I wanted to turn to something, obviously I know many of you at UMass Amherst are interested in, which is healthcare. This is a very large federated database or data set. Right now, there are 600 million unique patient records in this data set, which is called Odyssey, Observational Health Data Sciences and Informatics. Think about, this is 600 million EHRs. And the computer science audience, you will very much appreciate, this is 600 million EHRs in the same format. So you know how difficult it is, even in the United States, for our different healthcare providers and agencies and doctors and clinics to even share the same format. Well, imagine if they did. And so this is really quite a stupendous feat on the effort of the Odyssey group. It does involve 25 countries, over 200 researchers, 80 databases. So this is a huge, huge data set. And once you have all this observational data, you can ask questions and discover new things that you couldn't imagine and you couldn't possibly do through clinical trials. And so now what you want to really be able to do is use this observational data, complementing clinical trials and experimental data to really push forward healthcare. So what they did was they looked at 3 different diseases, diabetes, hypertension, and depression. And I like to show this slide because it makes my point that I made earlier about how data visualization is not enough. You need data interpretation. And so now I'm going to tell you how to interpret these beautiful pictures. So each ring of circles and here you see a ring of circles, stands for a particular clinic, and they looked at multiple clinics around the world. This is the Columbia University Medical Center, and each ring of circles, each radius in each ring of circles stands for one patient. And if you go from the center of the ring of circles to outwardly, the first ring you hit is the first drug that you are treated with for hypertension. This drug here, which I can't pronounce. If that drug doesn't work, then you're treated with a second drug, and that's indicated by the second circle in this ring. If that doesn't work, you're treated with a third drug, and that's indicated by this color here. If that doesn't work, you're treated with a fourth drug, and so on and so forth. Now, all these rings of circles that I'm showing you are cut off at 4, but some of them go out to many, many drugs. In other words, if you have hypertension and you're at the Columbia University Medical Center and you're in this database, I can tell you what sequence of drugs you were given to treat hypertension. So now, what are 2 interesting observations that the researchers were able to make by just looking at this data? The first is that if you collapse all these rings of circles just for hypertension, and I put up all the patients together, all those people who are treated for hypertension that we had data on in this data set, it turns out that 1/4 of the people are treated uniquely. In other words, if you're treated for hypertension and you're in that 1/4, and I'm your doctor, and you say, Jeanette, is there anyone else in the world being treated like I am? The answer would be no. And this was actually quite a surprise, quite astounding. And one then asks, well, why is that? And you have to go back and you know, those are interesting questions to answer from a medical and healthcare point of view. Another interesting observation that was made, and this again pops out at you when you look at the data, is that they looked at the rings of circles for diabetes, and for almost all of the rings of circles, they almost all looked like the first 2, where this chartreuse colored drug, if you will, the drug that the chartreuse color stands for, is the first line of attack, and for the most part it works, except for this bottom ring of circles. And this actually came from a Japanese clinic, where you see that chartreuse drug is not always the first line of attack, and for the most part it doesn't always work. And they tried to understand, well, what is going on here? And it turns out that the Japanese are genetically disposed against this particular metformin drug. So either the doctors know not to prescribe this, or when they do, they realize it's not going to work. So all of this just came out by looking at the data. It was not hypothesized, these two points I just made. So now let me turn to the Deconfounder. So when you have a rich database like this, you can do some interesting analysis and interesting modeling. So of course, I'm going to close with the story by putting the 2 pieces together. So I started talking about Deconfounder, and of course in medicine, there are multiple confounders all over the place, multiple causes for a particular effect. And it would be nice to tease out how much of a cause is part of that effect. And so that's what these researchers did, looking at the Odyssey data set. And let me just very, very shortly, briefly say that what they looked at is the treatment effects on hemoglobin, this particular protein that's an indicator for type 2 diabetes. And I'm writing here the model without the deconfounder, the model with the deconfounder. And the bottom line is, when you have the deconfounder actually reduces both false positive and false negative rates. What's meant by that is all these lines here in the chart on the left is a particular drug. And for a particular drug like acetaminophen, which is like aspirin, it basically turns what is thought to be causal to be non-causal. And vice versa happens as well. There are drugs like these two, molybdenum and hydrochlorothiazide, that are thought to be non-causal but turn out to be causal when you have the deconfounder. Now, it's hard to validate all of these results, so the best they could do to validate it was to argue that these results identify effective causal drugs that are more consistent with the medical literature. So I'm going to stop now and just remind you of my 3-word tagline, data for good. Thank you very much.
Thank you, Jeanette. I'll clap for everyone. It's been very interesting. We have a couple of questions that came in while you were speaking, and I will see if I can get those participants to ask those live, and I'll need to enable their mics. Just a minute. So first up is David Jensen, and you're on. So if you unmute, you should be able to ask Jeanette your question.
Excellent. Can you hear me?
Yes.
Okay, first, wonderful talk, Jeanette. Thank you so much for coming. And it's a great topic. And I'm particularly thrilled that you're highlighting the importance of causal inference, because I completely agree with you about its importance and its relevance to other fields. My question is really about the complexity of many data science methods. They can be applied in ways that are ill-informed or even intentionally biased to reach particular conclusions. And in conventional machine learning, where we're just doing prediction, we can just say, well, let's get a test set and see how well it does. In causal inference, that's not the case. As you point out, validation is very hard. And your example of the deconfounder, I think, is a particularly relevant example, because there are a set of restrictive assumptions, and there's also a set of design choices that provide an analyst with a lot of latitude. Just last week, David Bly in a talk said that the deconfounder is not a turnkey solution to causal inference, and I completely agree with him, and I think it's good to note that. How do we protect against motivated misuse of data science methods?
Well, it's interesting that you qualified that with motivated misuse, because there's misuse because of just ignorance or eagerness, and there's motivated misuse because of malicious intent. I suppose in both cases, one could be motivated for good or bad. I think we have as a community, we have a long way to go to explain, forget the motivated part, just to explain when is it appropriate to use this particular method or not. And if you do use this particular method, what can you really, how should one circumscribe the results so that you don't over claim a generalization or overclaim a result. And I think we are not there yet. I saw this when I was at Microsoft. We were like delighted and like, wow, face recognition, it's a solved problem now. Not even thinking about, the potential bias of the use of the technology and the fact that, training these face recognition systems were trained on biased data and so on. We were just so happy that the technology could, progress so quickly to solve a seemingly difficult problem. So now I think we, in the technology community in academia and industry, are taking that step back and being more reserved in how we want to prescribe the uses of our methods and our technology to others. It is certainly our responsibility to do that. I don't know that everyone does, but I completely agree with you, David. I think we need to be careful. And I especially think about my astronomer friends who just throw CNNs at anything and say, wow, we got these great results. And we can't even help explain the results for them. So
Right.
that seems a little, now maybe for astronomy, you know, maybe it's the universe and whatnot, it's okay. But for healthcare, when it's a radiologist, you know, taking for granted whatever that CNN spits out, that's more dangerous because that's life critical. And I think actually the medical community has been trained to be very conservative anyway. So they are going to be wary of us technology people. But it's an opportunity for us in technology and computer science, AI, data science, to actually, you know, figure it out so we know what we can say and we can make our assumptions crystal clear. And then make sure that the uses of our technology are used well, but also interpreted in a meaningful manner. It's not easy. We're not there yet.
Thank you.
Okay, we have a pending question from Will Lee. Will, I'm going to let you talk now. Oops. If you unmute, you should be able to speak, Will.
Okay, thank you. Hi, Professor. Nice to meet you. So you mentioned that in one of your slides, education is kind of one of the cross-cutting centers. I wonder if you can talk about maybe how education, or I should say how data science is applied in education today, and also what are some of the challenges that you might see down the road for educating the next generation about, you know, data science or computer science? Thank you.
It's a great question, Will. So first, let me just share with you the scope of the education working group or cross-cutting center. I'm amazed that your eye actually picked up on that because I flashed that slide up so quickly. First and foremost, there's a huge amount of interest in data science at Columbia throughout the entire university. So we, you know, there are courses, there are programs, there are curricula offered that touch upon data science, AI, machine learning, data methods, and so on. And so what this education group it's really faculty from across the university who are very interested in educating students in their discipline with data science methods. So for instance, in biostatistics, there's a huge push right now for certificate programs, you know, potential minors and so on in data science, along with biostats master's programs and even PhD programs and so on. And you name it down the line. So first, the education working group is really bringing together like-minded people. But we also have people, as you're suggesting, who are interested in using data science for education, for bettering our understanding of how to educate, how students learn, how teachers should better teach. We have a whole teachers college at Columbia University, and they have been hiring very recently some data scientists and computer scientists, so people who are interested in education technology, people who understand that for good or bad, one can actually collect a lot of data about students if they're online, and we can, you know, monitor how well they're doing. And you know, this is not new. The many companies, startups, government agencies, and so on have been doing this in their own way for education technology, using sequential decision making and reinforcement learning to better know, you know, what next exam question to present to student, how to intervene and help a student when the student is struggling. So all of those are really fair game for data science and education. And now let me turn to the other part of your question, which is what should we be teaching our students in data science? This is not an easy question to answer. You know, I think every university struggles with this, continues to struggle with this. At Columbia, we have a very rigorous master's program in data science, and so it's been on the books since 2012. It's one of the most rigorous master's programs, period, because it has so many required courses, and 7 of the courses are all technical. 3 in computer science, 3 in statistics. There's a capstone course, and all the students, when they take electives, they typically take more technical courses. So these students are highly trained in a very rigorous manner. But I am quite interested in making sure that data science, first of all, is not viewed as just about computer science, statistics, and machine learning and so on, but that it's important to be working with a particular domain, a data set in a particular domain. And so one has to actually either be a domain expert or work with a domain expert to really be a data scientist. This is not easy to teach. There are courses that we can offer, like the capstone course, which can give the students an opportunity to do that. But it's not clear how much domain expertise should be part of a curriculum or not. I think that what the Collaboratory does shows that one can bring data scientists and domain experts together. What Berkeley's Data 8 course does is something similar. And so that's just the foundations and the domain area. And I still think that when I think of, I helped start this Academic Data Science Alliance a few years ago. It's going great guns, but I'm seeing this really plethora of different approaches to what should we be training and teaching our students. And so I don't think there's an answer yet. And finally, just to add to all of that is the point I made earlier, which is I think we need to be teaching ethics to our data science students from day one. What I mentioned early in my talk is what's new about data today is it's data about us, data about people. And when you're talking about data about people, and you're talking about companies that are collecting this data about people, and right now they're not regulated, one has to be making sure that the students who eventually go work for these companies do have an ethical framework to be thinking about what it is they're doing. And so I think this is happening organically, even if you think about the tech companies like Google and Facebook and Amazon and Microsoft, and the employees in those companies now speaking up in ways that perhaps employees of companies 20 years ago would never do. So I think people are understanding the importance of ethics in data science. And this is something that I think we should be doing in computer science, but for sure in data science, be teaching ethics.
So I wanted to follow up on that one, Jeanette, while we give an opportunity for folks to type questions in. So what and how do we teach ethics, right?
It's a great question.
That's a tough one.
Yeah. Elliot, so it's a great question. I'm glad you're asking, because I don't have a good answer. I do have different models of how people are trying. And I think we're still in the experimental exploratory phase. So in terms of models, there's some obvious ones. One is you have a course on the side, everyone's required to take it. And the disadvantage of that is people compartmentalize it. A completely different model is you integrate ethics with every single course. And that's kind of the approach that we're trying to do at Columbia. We have some faculty who are game for integrating ethics in like their machine learning course, their database course, I can't remember, some other course. And then so slowly it's like integrating ethics throughout in this case, computer science curriculum. So that's one way to do it. It's actually not a bad idea. It's almost easy enough to do if you put your mind to it. Because whenever we're teaching anything, we are always giving examples. So one can always use examples as a way to ask an ethical question or ask a question about fairness in data collection. So one just needs to put one's mind to do it. So we have a very interested faculty in working with that model. So an in-between model, and this is something I get from some of my colleagues like Dana Boyd at Microsoft Research, which is you should teach ethics when you're for data science, when you're actually working with a real data set. So the opportunity for us in the Columbia is through the Masters of Data Science Capstone Project, where we have industry bring in a real world data set, or sometimes faculty do it, and teams of students work on this real world data set. And it's at that point where you can have a conversation about the data. Who collected this? Who gets to see it? Why did you collect it? Et cetera, et cetera. You can start asking those ethical questions. Now, let me try to address your more difficult question, which is what actually should we be teaching? There are different models of teaching, and we'll figure that out, or we'll do all 2 or 3 or whatever. And what might make sense for one school will be different for another. But the question is, what should we be teaching? So first of all, I struggle with this myself, because I thought, well, there are new ethical questions that are coming up with the technology that we're inventing. And this, by the way, this issue first hit me when I was at Microsoft, and we released this chatbot called Tay, and within 24 hours, we had to take it down, because it started reflecting the ugliness of the internet dark world, and basically retweeting and having Tay repeat all sorts of very offensive remarks, offending every subpopulation you could imagine. So we had to take her down. And that's when my eyes opened and said, oh my God, we're not even thinking about these things. And how could we not have even foreseen that? We should know better. We need to do better. So,
right.
So now what do we? Now, at first I thought, oh, technology invents new ethical questions. But then I did a little homework, and I realized, there are 2 frameworks that I think we can at least use as a starting point. One is the Belmont Report, which was written in the context of medical ethics, but it still identifies certain ethical principles like beneficence and justice, that if you think about it, these technologies like chatbots actually can be ethical questions can be characterized in terms of these same ethical principles. So in some sense, why reinvent the wheel? And there's another framework, now I'm forgetting the name of it, I can look it up right away, but that came out of actually the somewhat ethics of IT and the military, I think. I can't remember the name of the report, but the point is we actually have 2 very good starting points. And then one can ask for a given technology. Like there's the other canonical ethical question is self-driving cars. Do you run over, one old person or 6 young children? And there's no right answer to that, right? But someone has to answer that question if they're going to implement a decision-making system that has to operate in real time. So there are these ethical frameworks that identify these principles, which we can go back to and say, for our given technology, are we abiding by these principles? So I would say, let's start with the frameworks we have. And as we realize technology is introducing new ethical principles or new ethical questions that cannot be named by any of these principles, then we have then added to the ethics research.
Right. Yeah, thank you for pointing to that. Meanwhile, another question has come in. Yair, I'm going to allow you to talk to ask it yourself. You'll have to unmute.
Hello. Thank you. It was a very nice and interesting talk. I have a short question. So you talked a little bit about trustworthy machine learning, trustworthy AI. And my question is, how much can we self-regulate as industry and academia, and how much do we need to have an external regulatory body like I don't know, an FDA for algorithms or something like that? And what's your views on that, and what concrete steps should we take if given this problem?
Yeah, it's a good question. It's very timely, especially with movies like The Social Dilemma and Coded Bias coming out that in fact are arguing for very much what you just said, an FDA for AI. I think there's no way getting around it. I think there has to be some kind of regulation. I don't know what it would look like. I don't know how deep into the trenches of the companies it needs to be. But I have seen that regulation, although it may sound very onerous to companies, ends up having a positive effect. And let me just pick on the EU GDPR. And I was at Microsoft when that came upon us, and all of a sudden, a lot of engineering had to stop because we had to figure out, well, what does it even mean to delete someone? We know from a technical point of view, it's impossible to really do a full-fledged digital delete, but we needed to satisfy this GDPR in some meaningful way. And so in the end, even though a lot of the privacy regulations from the EU were onerous on major companies like Microsoft and so on, it did serve a purpose. It made the companies sit up and pay attention, and because it would hurt their bottom line. And so I think it made them actually, do their best to invent new technology internally for auditing, internally for, satisfying best effort for all the pillars of EU GDPR. So in the end, it had a positive effect, even though it did seem quite onerous. Now, the question is, what should the US do and how should it do it? The day after the election, I can't really speak to how this would happen, but we certainly know that Congress is interested. And I do think that it's probably for the benefit of citizens and consumers, it's probably insufficient to expect companies to self-regulate. It would be a little different if a sector were able to come up with provisions for themselves and then abide by that. But I also don't see that being strong enough and enough of an incentive. I think there's goodwill. So for instance, after the Tay incident at Microsoft, my colleague Eric Horowitz got together counterparts at Facebook and Google and DeepMind and so on, and started what has now become Partnership in AI. And they were really keen on trying to have the tech sector speak openly and transparently about the importance of using AI for good and making sure we respected customers' rights to privacy, et cetera, et cetera. This partnership in AI has really grown, but it's not like they can come up with rules and every company that's a part of the partnership is going to say, yes, we will abide. So I do think that a little regulation for government may be required for the future, for proper behavior. I just don't know what it would look like.
Okay, thank you very much. I think you've answered all the questions, and I'll applaud again. Thank you.